Another way of representing the enthalpy change in a chemical reaction is to use what's called an enthalpy level diagram. It's kind of like what we talked about before when you have those energy profiles where you go whoop, and that is an exothermic reaction, or one that goes like this, and that is an endothermic reaction. Pretty similar to something like that. It just gives you a little bit more clarity on what is endothermic and what is exothermic. Again, we should already know this, that in an endothermic reaction, which again is here, endothermic, we can see, again, these are the products, these are the reactants, that the enthalpy of the products is greater than the enthalpy of the reactants, and therefore delta H is absolutely positive. And again, that's the definition of an endothermic reaction. What that means is it means that energy is absorbed by the reaction from the surroundings as it occurs. So as the reaction happens, the water gets colder, or your hand gets colder, or it takes some heat from something else in order for this to happen. Again, that's why they typically feel cold. Remember, something like boiling water is an endothermic process. You think, well, wait a minute, it's hot. It's hot because you heated up the water. But what is the water doing? It's absorbing the heat from the flame, from the burner, from whatever, allowing those molecules, the water molecules, to break free from each other and turn from a liquid into a gas. And anytime you go, again, solid to liquid or liquid to gas, that is an endothermic process. Okay, and again, here you can see the products, delta H, that means positive there, are greater. The enthalpy of the products is greater than the reactants. And then down here, we've got our exothermic one, so that one would go down here. Again, the enthalpy of the products is less than the enthalpy of the reactants. Delta H absolutely is a negative value. And that means that energy is released. And a lot of times when that energy is released, the released energy is used to keep the reaction going. That's why, in general, if you think about which reaction is more likely to occur, exothermic reactions are absolutely more likely to occur than an endothermic reaction, because the energy that they produce, that they release, can be used again to break those bonds of the reactants and keep that reaction going. Whereas an endothermic reaction, if it doesn't have enough energy, no matter what, it's simply not going to start. If you can't overcome that activation energy barrier, the reaction won't even begin. Okay, and again, like up here, a gas to a liquid or a liquid back to a solid, those again are always, you have to lose energy or lose heat for that to happen. Delta H is a negative value. Okay, most of the time when we talk about delta H, you see a little degree sign up in the corner. And what that degree sign means is basically means that you're at standard conditions. Usually not a big deal, doesn't really mean anything. We will talk about some other things that sometimes aren't at standard conditions, but delta H typically are at standard conditions. When that happens, the pressure is just, again, atmospheric pressure, just our normal pressure around us. Concentrations are at 1 molar, and the temperature is at 298. Okay? And again, there's that little degree sign. We can see it right there, and that is the standard state. Okay, kind of like standard temperature and pressure with gases, STP, where you've got two set that. But notice on that one, so let's make sure we clarify that STP for gases are not the same. It is 1 atmosphere of pressure, but the temperature at STP with gases is 273 Kelvin. Everything else from here on out will be 298, which again is 25 degrees Celsius, which is about 77 degrees Fahrenheit. That's what they consider room temperature, is those temperatures right there, which they're all equal to each other. Okay. So, for example, the enthalpy of formation in the standard state is the enthalpy change of formation. So something, again, forming from its elements at 1 atmosphere of pressure or in a 1 molar solution at 298 Kelvin. Okay, here's just another way to look at endothermic versus exothermic. Remember, the system is just the reaction itself. The surroundings is everything else around it. The water, glass, air, thermometer, whatever. Anything else that's not directly part of the reaction is part of the surroundings. So when you feel a reaction, it feels cold. That's because it's taking energy from these to go into the reaction. And again, that's an endothermic process. When you feel, and again, why does that happen? Because it takes more energy to break the bonds in the reactants than the amount of energy that gets released when the products are formed. And in this case, when the reaction is releasing heat, that's again because the amount of energy that's released when those new bonds are formed is greater than the amount of energy it takes to break those bonds. Okay, last one, again, we kind of talked about this already, is many times they'll tell you a little bit about the reaction simply by putting that right there. Again, we talked about vaporization. Sometimes they do FUS, which is fusion, which is the same thing as melting. There's lots of different delta H's that they can use, okay? So delta H of combustion is obviously it has to burn. It has to react with oxygen. And in this case, we can see that the enthalpy change for that reaction is negative 1565 kilojoules per moles of reaction. And again, that means if 1 mole of, this is ethane, if 1 mole of ethane reacts and 3 moles of oxygen react, you're going to get 2 moles of CO2, 3 moles of water. Remember that mole of reaction thing, that's really important. Okay, and again, anytime you have just a carbon, hydrogen, and oxygen, if this only has carbon and hydrogen or carbon, hydrogen, and oxygen, the products are always just going to be CO2 and H2O. So what do standard enthalpy of combustion reactions look like? Well, let's see, the combustion of C5H12 going to react with O2 and make CO2 and H2O. And then we could balance that, and we would say 5 CO2s, 6 H2Os, and 8 O2s. There's 16 oxygens on the right-hand side. Okay, what about carbon monoxide? What's the combustion of carbon? Again, anytime something reacts with combusts, it reacts with O2. So could it make H2O? Well, there's no hydrogen in there, so absolutely not. What's the only other product it could make? Carbon dioxide. Okay, and then again, we would have to balance that. We put a 2 there, put a 2 there. It's balanced. Okay, and then hydrogen. What about when hydrogen burns? Again, here we don't have any any carbon, excuse me. So in that case, we can't have CO2. So what's it going to make? Just H2O. Okay, and then to balance that, we need a 2 here, and we need a 2 there. Okay, and then our last one would be aluminum. Well, wait a minute, aluminum, yeah, I mean, most things can burn. Think about magnesium. Magnesium is that one that when it burns, it produces that super duper bright white light. Okay, and that produces MgO. Okay, and usually when it's not just carbon like this, usually it will just be a synthesis reaction. So when aluminum reacts with oxygen, it's just going to create aluminum oxide. Aluminum has a +3 charge, oxygen's -2, so you switch those. And then we need a 2 there, a 3 there, and a 4 there. And then up here, kind of the same thing. Okay, so combustion reactions, again, typically if it has carbon, hydrogen, or carbon, hydrogen, and oxygen, it's going to make CO2 and H2O. If it's missing one of those elements, then it's only going to make CO2 or H2O. And if it's just something, just one random metal element reacting with oxygen, again, and they tell you it's a combustion reaction, because remember, Fe plus O2 makes Fe2O3. That's not a combustion reaction. Okay. Now, how would you know that? They would have to tell you that. They would have to tell you that aluminum burns in air. Or here they would say iron reacts with oxygen in the air to create rust. Okay. Again, not a combustion reaction, but you wouldn't be expected to know that without some additional information there. Again, we can balance this one too. Look, something like that. But Fe2O3, that's the chemical formula of rust. When your wheelbarrow or your shovel gets all rusty, or your bicycle, that's because the iron reacts with the oxygen in the air when there's a lot of moisture in the air to create Fe2O3. Okay? And we will start this next stuff in our next video.